For centuries, humanity has looked into the night sky and wondered how the universe began, how it evolved, and where it is ultimately heading. Every distant galaxy contains information about that enormous story. And with the James Webb Space Telescope, astronomers now have a powerful new way to examine some of the oldest light ever detected. JWST can observe extremely distant objects whose light has been traveling toward Earth for billions of years. That means looking deeper into space also means looking further back in time. But when scientists examine this ancient light, they sometimes encounter observations that challenge their expectations. One of the most dramatic ideas surrounding these observations is the apparent disappearance of enormous numbers of stars and galaxies from our accessible view. To be clear, this does not mean that hundreds of trillions of individual stars have suddenly vanished from existence. The real issue is much more fascinating. The universe is expanding. And because that expansion is accelerating, extremely distant regions of the cosmos can eventually become unreachable to us. Their light may continue traveling through space, but there is a limit to whether light emitted in the future will ever be able to cross the expanding universe and reach Earth. This creates a strange cosmic effect. A galaxy can exist physically while gradually becoming impossible for us to observe. Its older light may still be arriving. But new light released from that galaxy may never reach us. To understand why, we have to understand redshift. When light travels across an expanding universe, the wavelength of that light can become stretched. The farther the light has traveled, the more pronounced this effect can become. Astronomers measure this stretching and use it to learn about the motion and history of distant galaxies. But there is something deeper happening. The galaxy is not necessarily racing through space away from us like a rocket. Instead, the space between distant regions is expanding. Imagine 2 points drawn on a sheet of rubber. If the rubber stretches, the points become farther apart even though neither point is actively moving across the surface. On cosmic scales, something similar happens with expanding space. The farther apart two regions are, the more significant the expansion between them can become. And over immense distances, this has extraordinary consequences. The observable universe is enormous, extending tens of billions of light-years in diameter. Yet not everything inside that enormous volume will remain permanently accessible. Dark energy appears to be associated with the accelerating expansion of the universe. Current cosmological models indicate that dark energy makes up roughly 2/3 of the universe's total energy density, while dark matter accounts for most of the remaining dark component. Ordinary matter, the stars, planets, gas, dust, and everything we can directly interact with, represents only a small fraction. That means most of the universe is composed of things we still do not completely understand. And dark energy is one of the greatest mysteries among them. We know that the universe's expansion has accelerated. But we still do not know the fundamental nature of dark energy. Is it a property of empty space? Is it something more complicated? Could our understanding of gravity require modification on the largest scales? These are active scientific questions. JWST contributes to this investigation by observing distant galaxies and measuring the ancient light reaching us. The farther astronomers look, the further back in cosmic history they can investigate. And every measurement helps researchers reconstruct how the universe expanded over time. This is where the idea of a cosmic horizon becomes so important. There are regions of space whose future light will never reach Earth because the expansion of the universe separates us too rapidly. From our perspective, those regions can gradually fade from observational reach. The universe is therefore doing something that feels almost impossible to imagine. It is not simply getting larger. It is creating an ever-changing boundary around what humanity can ultimately observe. And that raises a profound question. How much of the universe will remain visible to future civilizations? The answer may be very different from what the night sky looks like today. And that brings us, the universe we see today is not necessarily the universe that future civilizations will see. As cosmic expansion continues, increasingly distant galaxies can move beyond our ability to receive new information from them. Their ancient light may remain visible for an enormous amount of time. But eventually, the universe around us could appear increasingly isolated. Galaxies that are not gravitationally bound to our local cosmic neighborhood may gradually disappear from view. This does not mean those galaxies are physically destroyed. They are still there. The problem is communication. The expanding space between us and them can become so great that light emitted at later times will never complete the journey to Earth. It is almost as though the observable universe is slowly becoming an island surrounded by an expanding ocean. That idea has profound consequences for astronomy. Imagine a civilization billions of years in the future. If it remains isolated within a gravitationally bound group of galaxies, it may see a much darker sky. Many of the galaxies we observe today could have become permanently inaccessible. Future astronomers might have far less evidence that the universe was once filled with countless distant galaxies. They could see their local cosmic environment and have difficulty reconstructing the larger universe we know today. This is one reason the observations of modern telescopes are so valuable. We are living during a remarkable period in cosmic history. The universe is old enough for galaxies, stars, planets, and complex chemistry to exist. Yet much of the distant cosmos is still observable. We can study galaxies billions of light-years away. We can measure their redshifts. We can examine their chemical compositions. And we can use those observations to reconstruct the history of cosmic expansion. But the source material behind the idea of 900 trillion disappearing stars should not be interpreted literally as a confirmed JWST discovery of stars suddenly disappearing. There is no established observation showing that JWST watched hundreds of trillions of stars vanish without remnants. The more scientifically meaningful story is about cosmic horizons and the long-term consequences of accelerated expansion. That story is already extraordinary enough. It tells us that the universe has a built-in observational limit. And that limit changes with cosmic time. The idea also raises another fascinating question. Could our current understanding of cosmic expansion eventually change? Scientists have repeatedly refined their models when new evidence appeared. The discovery that cosmic expansion is accelerating was itself a major turning point. The unknown component associated with that acceleration became known as dark energy. But its physical nature remains unresolved. Perhaps future observations will reveal that dark energy behaves exactly as current models predict. Perhaps its properties will turn out to be more complicated. Or perhaps an entirely new framework will eventually be required. This is why observations matter more than speculation. A dramatic theory is only useful if nature provides evidence to support it. For now, ideas involving mysterious cosmic transformations, advanced civilizations hiding entire regions of space, or fundamental changes to reality remain speculative. They can make fascinating science fiction stories. But they are not established explanations for cosmic expansion. The real mystery is already enormous. We live inside a universe that is expanding faster than it once did. We know that distant galaxies can become permanently unreachable. We know that dark energy appears to dominate the large-scale evolution of the cosmos. And we know that the light reaching our telescopes is often a message from a universe that existed billions of years ago. That makes every observation a race against cosmic time. The stars and galaxies visible in our sky today will not remain visible forever. Some distant objects will eventually cross beyond our future observational horizon. And as that happens, the universe accessible to us will become increasingly limited. But there is also something inspiring about this. Humanity exists during a remarkable window in cosmic history. We have developed instruments capable of collecting ancient light from the early universe. We can analyze the chemistry of distant galaxies. We can measure cosmic expansion. And we can ask questions about the ultimate fate of everything we see. The universe may continue expanding for an unimaginably long time. The distant sky may eventually become darker. But right now, the cosmos is still speaking to us through ancient light. Every photon arriving from a distant galaxy is evidence that the universe has a history. And every telescope that captures that light gives humanity another opportunity to understand it.